You've probably heard people say that time is constant, that a second is a second, no matter where you are, no matter what you're doing. And I want you to pause for a moment and really feel how natural that sounds, because everything in your daily experience tells you it must be true. Clocks tick forward, days pass, causes come before effects, and nowhere in your life does time seem to bend or stretch. So when I tell you that this intuition is wrong, not slightly wrong, but fundamentally broken, you should feel a little uncomfortable, because that discomfort is exactly where physics begins to get interesting. Now imagine you're standing still, and I throw a ball forward to you. The ball has some speed. Simple enough. But to someone watching from the side, if I were already moving, the speeds would add together. And this is how the world seems to work. Everything stacks neatly. Motion on top of motion. And no surprise. Just clean arithmetic. And for centuries, this was the foundation of physics. A comfortable, intuitive picture built by Newton, where space is a stage and time is a universal clock ticking the same for everyone, everywhere. But now I want you to take that same intuition and apply it to light, because this is where everything starts to crack. Imagine you're on a spaceship moving incredibly fast, and you shine a flashlight forward. What do you expect to happen? Really think about it, because your instinct will tell you the light should move faster relative to someone standing still, just like the ball did. But nature refuses to cooperate, because no matter how fast you are moving, no matter how you chase it, measure it, or observe it, light always moves at exactly the same speed, about 300,000 kilometers per second. Not approximately, not on average, but precisely the same for you and for everyone else. Now stop there, because that one fact alone should bother you deeply, because it doesn't fit into the world you thought you understood. How can two observers moving relative to each other both measure the same speed for the same beam of light? Something has to give. And Einstein realized that it wasn't the light that changed, it was everything else. Space and time themselves had to adjust. Let me say that again, slowly. Because this is the moment where intuition collapses. Space and time are not fixed backgrounds. They are flexible. And they rearrange themselves to keep the speed of light constant. Which means that if you start moving fast enough, time for you literally slows down relative to someone else. Not as an illusion, not because of your perception, but physically, measurably slower, and distances in the direction you're moving actually shrink, as if the universe is quietly compressing itself just to preserve this one rule about light. You might think this is just a strange theoretical idea, but it isn't. We've tested it over and over again, with particles moving close to the speed of light that live longer than they should, with atomic clocks flown around the Earth that fall out of sync exactly as predicted. And every time the universe gives the same answer. Time is not universal, and space is not absolute. Now, I want you to consider the consequence of this, not as an equation, but as a reality you're living inside right now. Because if time depends on motion, then there is no single shared now across the universe. When you say something is happening right now on a distant star, that statement doesn't actually mean anything absolute. Different observers will disagree about what now even is, and not because they're mistaken, but because the structure of reality itself doesn't provide a universal present. This is the part where things start to feel unstable, because you've lost something you didn't even realize you were relying on. a global sense of time that ties everything together and in its place. You get something far stranger, a woven fabric of space and time, where measurements depend on how you move through it, where simultaneity breaks apart, and where the idea of a single ticking clock for the universe simply does not exist. And here's what makes this even more fascinating. If you could travel fast enough, close to the speed of light, you could leave Earth, journey to a distant star, and return to find that far more time has passed here than for you. Your friends older. Your world changed. While you've only experienced a fraction of that duration, not because you've cheated time, but because time itself does not flow the same way for everyone, and never did. So now I want to ask you something, and I want you to really sit with it, because this is not just physics. It's a shift in how you see reality. If time is not absolute, if space is not fixed, if even the idea of now depends on how you move, then what exactly is the stage on which the universe exists? What is this thing that bends and stretches and rearranges itself just to keep light consistent? What is space-time? Really, not as a word you've heard before, but as something that defines everything you experience. Because once you start asking that question, you've already left the comfortable world behind, and you're stepping into a place where intuition fails, where reality is stranger than anything you would have guessed, and where the deeper you go, the less certain everything becomes. And that, whether you like it or not, is exactly where the real story begins. So now you're standing in a universe where time can stretch, space can shrink, and nothing feels quite as solid as it used to. And just when you think things couldn't get any stranger, I want you to follow Einstein one step further. Because what he realized next doesn't just tweak your intuition, it completely rewrites what you think gravity is. Up to this point, gravity seemed simple, almost obvious. Things fall because something pulls them down. Newton gave it a formula. It worked beautifully. You could predict the motion of planets, the arc of a cannonball, the rhythm of the tides, and for more than 2 centuries. No one had a serious reason to doubt it, but there was a hidden problem sitting quietly beneath all of this. A problem you wouldn't notice unless you asked a very uncomfortable question. How does gravity act across empty space? Instantly, because that's what Newton's theory implied. If the sun were to suddenly disappear, Earth would immediately fly off, as if the information about the sun's absence had traveled across space with no delay at all. And now you already know something that Newton didn't. Nothing can travel faster than light. Not signals, not force, not information. So gravity couldn't possibly work the way Newton described. Something deeper had to be going on. And this is where Einstein had what he later called the happiest thought of his life. Not a complicated equation, not a long calculation, but a simple mental picture. The kind of thing you can hold in your head if you're willing to really look at it. And I want you to picture this with me, because it's deceptively ordinary. A person falling off a roof. Now, don't think about the impact. Just think about the fall itself. Because in that moment, while they are falling, something remarkable happens. They don't feel their own weight. From their perspective, they are weightless. If they let go of an object, it doesn't drop away from them. It floats right beside them, falling at exactly the same rate. And this is not a trick, not an illusion. It's a real physical state. The same state astronauts experience when they orbit Earth, not because there is no gravity up there, but because they are in continuous free fall. always falling, never hitting the ground. Now here's the part that should stop you, because it stopped Einstein. If you were inside a closed box, no windows, no way to see outside, and you felt weightless, could you tell whether you were floating in deep space, far from any gravitational field, or falling freely under the influence of gravity? The answer is no. There is no experiment you could perform inside that box that would distinguish the two situations. They are physically identical. And now flip the scenario. Imagine you're inside a box again, but this time you feel a force pressing you to the floor. You drop an object and it accelerates downward. Everything behaves exactly as it does here on Earth. Now ask yourself, are you standing on a planet, or are you inside a rocket in empty space, accelerating upward at a constant rate? Again, there is no way to tell. The effects are indistinguishable. This is the equivalence principle, and it is much more than a clever observation. It is a statement about reality itself. Gravity and acceleration are the same thing. Not similar, not approximately equal, but fundamentally identical in their effects. And once you accept that, really accept it, the entire concept of gravity begins to dissolve, because now you have a problem. You already know from special relativity that acceleration affects space and time. It changes how clocks tick and how distances are measured. And if gravity is equivalent to acceleration, then gravity must also affect space and time. It cannot simply be a force acting within space. It must be something that changes the structure of space itself. So now I want you to let go of the idea that gravity is pulling anything at all, and instead imagine that space and time form a kind of fabric, not a physical material you can touch, but a geometric structure that can bend and curve. And when a massive object like the sun exists, it doesn't reach out and pull the earth. It changes the geometry of the space-time around it, creating curvature. And the earth, simply trying to move in the straightest possible path, finds that this straight line is no longer what you expect. Because in a curved geometry, straight paths can look like curves. Think about that carefully. Because this is the inversion that makes everything click. The earth is not being pulled into orbit. It is moving straight ahead through a space-time that is curved. And that straight motion traces out what we see as an orbit. Just as an airplane flying along a great circle route on Earth appears to curve on a map, even though it is following the straightest possible path on a curved surface. And suddenly, gravity is no longer a force. It is geometry. It is the shape of space-time itself, telling matter how to move in matter. In turn, telling space-time how to curve. A feedback loop so elegant that it replaces the entire Newtonian picture with something deeper and far more unsettling. But here's where I want you to pause again. Because while this idea is beautiful, it also raises a question that you can't ignore anymore. If space and time can bend, if they can stretch and curve depending on mass and motion, then what exactly are they made of? What is this thing that can warp and twist and yet remains invisible? And more importantly, how far can that bending go before the entire structure breaks down? Because once you start asking that, you're no longer just talking about gravity. You're standing at the edge of something much darker, where space-time itself can fold so extremely that nothing escapes, not even light. And that's where the story's about to take you next. Now, you've accepted something that would have sounded absurd just a moment ago, that gravity is not a force, but the bending of space-time itself. And I want you to take that idea seriously, not as a metaphor, not as a diagram on a textbook page, but as something physically real. Because the moment you do, a new and uncomfortable question appears almost immediately. If space-time can bend, how far can it bend before it stops behaving in any way we can understand? Because when you think about it, nothing in the idea of curvature puts a limit on how extreme that bending can become. And nature, as it turns out, is not shy about pushing ideas to their limits. So imagine taking a massive object, something like a star, and compressing it, squeezing it down, smaller and smaller, while keeping its mass the same. What happens to the space-time around it? The curvature increases. The distortion becomes stronger. And at some point, something extraordinary occurs. Not gradually, not gently, but as a kind of threshold, beyond which the rules themselves begin to collapse. There is a critical boundary, a radius, where the curvature becomes so intense that even light, the fastest thing in the universe, can no longer escape. And once you cross that boundary, there is no turning back, no path that leads outward. Every possible direction, you can move points inward, deeper into the curvature. And this boundary is what we call the event horizon. But I want you to understand what that really means, because it is not a physical surface you can touch. It is a limit in the structure of space-time itself, a point beyond which the concept of escape simply stops existing. Now pause and think about that carefully, because you're used to thinking of space as something you can move through freely. Forward, backward, up, down. But inside this region, those choices disappear. Not because something is blocking you, but because the geometry itself has been twisted so completely that all possible futures lead inward. And I am choosing that word deliberately. Futures, because inside a black hole, moving toward the center, is not just a direction in space. It becomes as inevitable as moving forward in time. And that brings us to the deepest part of the problem. Because if you follow the equations of general relativity all the way inward, past the event horizon, past any region we could hope to observe, they lead you to a point where the curvature becomes infinite, where density becomes infinite, where space-time itself collapses into something that the mathematics can no longer describe. And this point is called a singularity. But that name hides something important. It is not an object. It is not a place in the usual sense. It is a signal that the theory has reached its limit, that it has been pushed beyond the domain where it can make sense. This is where the elegance of Einstein's theory begins to crack. Not because it fails in the usual way, not because it gives wrong predictions, but because it predicts its own breakdown. It tells you that under extreme conditions, the very concepts it relies on, space, time, geometry, stop behaving in any coherent way. And that should make you uneasy, because it means that the theory we trusted to describe the universe is incomplete at its most fundamental level. And here's the part that even Einstein himself resisted. Because when these solutions first appeared in the mathematics, they seemed like artifacts, strange results that couldn't possibly correspond to reality. Surely nature wouldn't allow something to collapse so completely that not even light could escape. Surely there must be some hidden mechanism, some pressure, some effect that prevents this extreme outcome. But as physicists pushed the equations further, and as they began to model the life cycles of stars, a different picture emerged, one that could not be ignored. When a sufficiently massive star runs out of fuel, there is nothing left to support it against its own gravity. No outward pressure strong enough to counter the inward pull, and the collapse becomes unstoppable, not slowing down, not stabilizing, but accelerating, compressing matter beyond anything we can recreate or observe directly. And the mathematics shows, again and again, that if the mass is large enough, there is no known force in nature capable of halting this process. The star must continue collapsing past its own event horizon, sealing itself off from the rest of the universe. So now you're faced with something deeply unsettling. Not just an exotic object in space, but a prediction that reality itself can form regions where our understanding breaks down completely, where the smooth fabric of space-time tears into something undefined. And this is not speculation anymore, because over the past decades, we have gathered overwhelming evidence that black holes are real. We see stars orbiting invisible masses. We detect energy pouring out from regions too small to contain anything else. We observe gravitational waves from their collisions. And every piece of data points to the same conclusion. These objects exist, and yet, even as we confirm their existence, the central mystery remains untouched, because everything we can observe happens outside the event horizon. We see the effects, the shadows, the distortions, but the interior remains hidden, forever inaccessible, not just practically, but in principle, because no information can come back out to tell us what truly happens there. So I want you to sit with that for a moment, because this is where the story becomes more than just physics. It becomes a question about the limits of knowledge itself. We have a theory that works with extraordinary precision, that predicts phenomena we can measure and confirm. And yet at its core, it leads us to a place where it stops making sense, where infinity appears, where explanation breaks down. And that is not a satisfying ending. It is an invitation, a sign that something deeper is waiting to be discovered. Because whenever a theory produces infinities, whenever it tells you that something becomes undefined, it is not the universe that is broken. It is your description of it. And somewhere beyond that singularity, beyond that mathematical failure, there must be a more complete picture. A way of understanding space-time that does not collapse under its own logic. And the search for that picture is what drives everything that comes next. Because once space-time can break, you can no longer pretend you understand what it truly is. Now consider the position you are in after everything we have discussed so far. Because the ideas of relativity might seem abstract when you first encounter them, but they are not confined to distant stars or extreme cosmic events. They are embedded directly into the systems you use every day, operating quietly in the background without drawing attention to themselves. Take GPS as a concrete example. A network of satellites orbiting Earth that continuously send timing signals down to receivers like your phone. And the entire system depends on measuring how long it takes those signals, traveling at the speed of light, to reach you. Because from that time delay you can calculate distance. And from multiple distances you can determine position. But this only works if the clocks involved remain synchronized with extraordinary precision. Here is where relativity becomes unavoidable, because the clocks on those satellites are not experiencing the same conditions as clocks on the surface of Earth. They are moving at high speeds relative to the ground. And according to special relativity, that motion causes their time to run slightly slower. But at the same time, they are farther from Earth's gravitational field, where gravity is weaker. And according to general relativity, time runs slightly faster in weaker gravity. So the system must account for both effects simultaneously. The result is not negligible. The difference accumulates to tens of microseconds per day. And if left uncorrected, that small discrepancy would translate into positioning errors of several kilometers, making the system unusable. So engineers incorporate relativistic corrections directly into the operation of GPS, adjusting the satellite clocks so that they remain aligned with clocks on Earth, ensuring that the calculations remain accurate. This is a practical application of a theory that also describes phenomena at vastly different scales, including objects like black holes and the structure of the universe itself. And yet the same mathematical framework applies consistently across all these contexts, which is one of the reasons it is considered so successful. Beyond navigation systems, there are experiments designed specifically to observe the dynamic behavior of space-time, one of the most significant being the detection of gravitational waves, which are disturbances that propagate through space-time as a result of accelerating masses, particularly in extreme events such as the merger of compact objects like black holes or neutron stars. Detecting these waves requires measuring incredibly small changes in distance, and instruments like LIGO are designed for this purpose, using long perpendicular arms and laser interferometry to detect minute differences in the time it takes light to travel along each path. When a gravitational wave passes through, it slightly stretches one direction while compressing another. And this produces an interference pattern that can be measured. The first confirmed detection occurred in 2015, when a signal consistent with the merger of two black holes was observed, and the characteristics of that signal matched the predictions made by general relativity, providing direct evidence that space-time can support propagating waves, and that these waves carry energy across vast distances. Another line of evidence comes from observations of black holes themselves, particularly through imaging techniques that combine data from multiple telescopes, such as the Event Horizon Telescope, which uses a global network of radio observatories to achieve extremely high resolution, effectively creating a telescope the size of Earth. The resulting images show a dark central region surrounded by a bright ring of emission, corresponding to matter orbiting near the event horizon. And the shape and size of this structure are consistent with the predictions of general relativity regarding how light behaves in strongly curved spacetime, including effects like gravitational lensing and photon orbits. What is being observed in these images is not the interior of the black hole, but the influence it exerts on the surrounding spacetime, which in turn affects the paths of light reaching the detectors. And by analyzing these patterns, it is possible to infer properties such as the mass and spin of the black hole taken together. These examples illustrate that general relativity is not limited to theoretical descriptions. It provides a framework that is both predictive and experimentally supported across a wide range of conditions, from satellite systems near Earth to astrophysical phenomena occurring billions of light years away. And in each case, the same underlying principles apply, describing how space-time responds to mass and energy, and how that response influences motion and observation. At the same time, while the theory accurately describes these effects and enables precise calculations, it does not provide a direct explanation of the underlying nature of space-time itself. It treats space-time as a continuous geometric structure whose curvature can be calculated. But it does not specify what this structure is made of or whether it has a more fundamental description at smaller scales. This creates a situation where the theory is both highly effective and incomplete in a conceptual sense. It works as a tool for prediction and measurement, but leaves open deeper questions about the nature of the entities it describes. And those questions become more prominent as one examines phenomena where the limits of the theory begin to appear. At this point, the question shifts from how space-time behaves to what space-time actually is. because everything described so far treats it as a continuous geometric structure, something that can bend, stretch, and propagate waves, but without specifying its underlying nature. And this becomes increasingly important when we consider that most other aspects of physics, particularly at very small scales, are not continuous at all. Quantum mechanics, which successfully describes the behavior of particles and fields, introduces a fundamentally different picture of reality, one in which quantities such as energy and angular momentum are quantized, existing in discrete units rather than forming a smooth continuum. And this raises a natural question. If matter and energy are quantized, should space-time itself also have a discrete structure at sufficiently small scales? One way to approach this question is through the concept often referred to as quantum foam, which suggests that if space-time is examined at extremely small distances, on the order of the Planck length, it may no longer appear smooth, but instead exhibit fluctuations due to quantum uncertainty, with geometry itself becoming dynamic and irregular, constantly changing in a way that has no classical analog. And while this idea is difficult to test directly, it provides a conceptual starting point for thinking about space-time beyond the framework of general relativity. Building on this, one of the main theoretical approaches is loop quantum gravity, which attempts to quantize space-time directly rather than introducing new fundamental objects in this framework. Space-time is not continuous, but composed of discrete elements, often described as networks or loops. And quantities such as area and volume take on quantized values, implying that there is the smallest possible unit of space, below which the notion of distance may no longer be meaningful. And this discretization could potentially resolve issues such as singularities by preventing infinite compression. However, loop quantum gravity faces significant challenges, particularly in connecting with other established theories, such as the Standard Model of particle physics, and in producing clear, testable predictions that could distinguish it from alternative approaches, which limits its current empirical validation. Another major framework is string theory, which takes a different perspective by proposing that the fundamental constituents of nature are not point particles, but one-dimensional objects known as strings, whose vibrational modes correspond to different particles, including those associated with forces. And in this context, space-time is not fundamental, but emerges from the interactions of these strings within a higher dimensional setting, typically involving additional spatial dimensions that are compactified at very small scales. String theory has the advantage of providing a mathematically consistent way to include gravity alongside other forces. And it naturally incorporates a quantum description of gravitational interactions through the existence of a graviton mode. But it also introduces a large number of possible solutions, depending on how the extra dimensions are configured, leading to what is often called the landscape problem, where many different versions of low-energy physics could arise, and it becomes difficult to determine which one corresponds to the universe we observe. In addition, the lack of direct experimental evidence for key predictions, such as supersymmetric particles, has raised questions about how string theory can be tested within current technological limits, since the energy scales involved are far beyond what can be reached in existing experiments, leaving the theory in a largely theoretical domain. A more recent line of thought suggests that space-time may not be fundamental at all, but instead emerges from deeper quantum relationships, particularly quantum entanglement. which describes correlations between particles that cannot be explained by classical means. And in some theoretical developments, these correlations are proposed to give rise to the geometric structure of space-time itself, implying that spatial relationships could be derived from patterns of entanglement rather than existing independently. This perspective is reflected in ideas such as the ER equals EPR conjecture, which explores a possible connection between entanglement and geometric links resembling wormholes, suggesting that connectivity in space-time may be related to quantum correlations, although these ideas remain under active investigation and are not yet part of a complete, experimentally verified theory. Across all these approaches, a common theme emerges, which is that the smooth space-time described by general relativity may be an approximation valid at large scales, but not at the smallest ones, and that a more fundamental description likely involves structures or relationships that differ significantly from classical geometry, whether in the form of discrete networks, vibrating strings, or entangled quantum states. Despite the diversity of these models, none has yet achieved both full theoretical consistency with all known physics and direct experimental confirmation, which means that the question of what space-time is made of, or whether it is made of anything in the conventional sense, remains open. And current research continues to explore these possibilities through mathematical development, indirect observation, and the search for phenomena that could reveal signatures of a deeper underlying framework. When the discussion turns to the origin of the universe, the framework of general relativity leads to a very specific conclusion, which is that if the universe is expanding today, then in the past it must have been smaller, denser, and hotter. And by extrapolating this expansion backward in time using Einstein's equation, one eventually arrives at a state where density and temperature increase without bound, a point often referred to as the Big Bang singularity. But it is important to understand what that term actually represents, because it is not a physical event described in detail, but rather an indication that the equations themselves are no longer valid under those conditions. Observationally, there is strong evidence supporting the idea that the universe has evolved from a hot and dense state, one of the key pieces of evidence being the expansion of space, which can be measured through the redshift of distant galaxies, where the wavelength of light is stretched as space itself expands during its journey toward us. And this relationship between distance and redshift indicates that galaxies are moving away from each other in a systematic way, consistent with an expanding universe. Another major line of evidence is the cosmic microwave background radiation, which is a nearly uniform bath of microwave radiation observed in all directions, interpreted as the remnant of an early phase when the universe was much hotter and filled with a dense plasma of particles and radiation. And as the universe expanded and cooled, it reached a point where electrons and protons could combine to form neutral atoms, allowing light to travel freely for the first time. And the radiation from that era has continued to propagate ever since, stretched to longer wavelengths by cosmic expansion. Detailed measurements of this background radiation reveal small variations in temperature, which correspond to tiny differences in density in the early universe. And these fluctuations serve as the seeds for the large-scale structures observed today, such as galaxies and clusters, forming over billions of years through gravitational amplification. And the statistical properties of these fluctuations match theoretical predictions with high precision, providing strong support for the overall cosmological model. However, When attempting to describe the earliest moments, the limitations of general relativity become apparent because, as one approaches extremely small timescales on the order of the Planck time, quantum effects are expected to become significant, and the classical description of space-time as a smooth continuum is no longer sufficient, which means that the singularity predicted by the equations should not be interpreted as a literal physical state, but rather as a boundary beyond which the current theory cannot provide reliable predictions to address some of the issues associated with the early universe. The concept of cosmic inflation has been introduced, which proposes that during a very brief period, shortly after the initial expansion, the universe underwent an extremely rapid exponential expansion, increasing its size by many orders of magnitude in a very short time. And this mechanism helps explain several observed features, including the large-scale uniformity of the universe, since regions that are now far apart would have been in close contact before inflation, allowing them to reach similar conditions. Inflation also provides an explanation for why the geometry of the universe appears to be close to flat, as rapid expansion would tend to smooth out any initial curvature. And it offers a mechanism for generating the small density fluctuations observed in the cosmic microwave background by amplifying quantum fluctuations to macroscopic scales, which then evolve into the structures seen today. Despite its successes, inflation does not resolve the fundamental issue of the initial singularity, because it still requires certain initial conditions to begin. And if one traces the history of the universe further back, the problem of describing the very beginning remains, indicating that a more complete theory, likely involving quantum gravity, is necessary to provide a consistent account of these earliest moments. Alternative ideas have been proposed, such as models in which the universe undergoes a bounce rather than beginning from a singularity, with a prior contracting phase followed by expansion, or scenarios in which the universe emerges from a quantum fluctuation, but these remain speculative and are not yet supported by definitive observational evidence. As a resulto, the description of the universe near time zero remains incomplete, with current theories providing a detailed account of its evolution after a certain point, but leaving the earliest phase, where classical and quantum effects intersect, beyond the reach of established models. And this region represents a boundary in our understanding, where existing frameworks must be extended or replaced to achieve a more comprehensive description of cosmic origins. The discussion of black holes becomes significantly more complex when quantum effects are taken into account, because within the framework of general relativity alone, a black hole appears as a region from which nothing can escape and in which information about what has fallen in is effectively inaccessible to an outside observer. But this picture changes when quantum field theory is applied in the presence of strong gravitational fields. Stephen Hawking showed that black holes are not completely black, but instead emit radiation due to quantum effects near the event horizon, a process now known as Hawking radiation. And this can be understood qualitatively by considering that in quantum theory, empty space is not truly empty, but filled with fluctuations in which particle-antiparticle pairs are constantly created and annihilated over extremely short time scales. And near the event horizon, it is possible for one particle of such a pair to fall into the black hole while the other escapes to infinity. From the perspective of an external observer, the escaping particle appears as radiation emitted by the black hole, and the particle that falls inward effectively carries negative energy relative to that observer, reducing the mass of the black hole over time, so that the black hole gradually loses energy and can eventually evaporate completely if no additional matter falls into it. This result introduces a fundamental problem when considered alongside the principles of quantum mechanics, because quantum theory is built on the idea that information is preserved in the evolution of physical systems, meaning that the complete description of a system at one time determines its description at any other time. And that information, while it may become highly dispersed or difficult to reconstruct, is never destroyed. However, Hawking radiation appears to be thermal in nature, characterized only by properties such as temperature and lacking any detailed information about the specific material that formed the black hole or fell into it. And if a black hole fully evaporates, leaving behind only this thermal radiation, then it would seem that the information about its initial state has been irretrievably lost, which would violate the principle of unitarity in quantum mechanics. This tension between general relativity and quantum mechanics is known as the black hole information paradox, and it has been the subject of extensive debate and research for several decades, because it suggests that at least one of the underlying assumptions in our current theories must be incomplete or require modification under extreme conditions. One of the key developments in addressing this paradox is the idea that the information associated with a black hole may not be stored in its interior in the way originally assumed, but instead encoded on its boundary, specifically on the event horizon, an idea that is closely related to the concept of black hole entropy, introduced by Jacob Bekenstein and further developed by Hawking, which shows that the entropy of a black hole is proportional to the area of its event horizon rather than its volume. This observation led to the formulation of the holographic principle, which proposes that the information content of a region of space can be fully described by degrees of freedom defined on its boundary, suggesting that the three-dimensional structure of space-time may in some sense be represented by a lower dimensional theory. And this idea has found support in certain theoretical frameworks, particularly in string theory, through correspondences such as the ad-CFT duality. Within this context, it becomes possible that the information about matter falling into a black hole is preserved in a highly scrambled form on or near the event horizon and is gradually released through correlations in the Hawking radiation. Even though the radiation appears thermal when considered at a coarse level, and recent developments involving quantum extremal surfaces and the concept of islands in space-time have provided mathematical support for this possibility. These approaches suggest that when calculating the entropy of the radiation emitted by a black hole, one must include contributions from regions inside the black hole that are effectively encoded in the radiation itself, leading to a behavior consistent with the expected Page curve, where entropy initially increases and then decreases as the black hole evaporates, indicating that information is not destroyed but redistributed in a complex manner. Despite this progress, a complete